Good afternoon to everybody. The title of the seminar today is Thermodynamic Stable Nanovesicles and their use in nanomedicine. The speaker is Dr. Guillem Vargas-Nadal. He is a nanotechnologist with experience in nanovesicles and nanomedicine. He studied nanoscience and nanotechnology at the Autonomous University of Barcelona, graduating in 2015. He later obtained a master's degree in biochemistry, molecular biology, and biomedicine at the same university. He then obtained his PhD in nanosciences at the Institute of Material Science of Barcelona and in the spin-off Nanomod Technologies. After finishing his PhD in 2020, he started a postdoc in the same institution and then moved to University of Parma for a second postdoc in the field of fluorescent organic nanoparticles. This year, he came back to ICMAB as a postdoc, also working as a project manager. Guillem, thank you for accepting our invitation, and when you are ready, you can share the screen and start. The floor is yours.
Thank you. Thank you for inviting me, of course, yes. I share the screen.
Yeah.
I think that you are viewing my screen.
Yes, it's fine.
Thank you. So I start the presentation as thank you, of course, another time. And as Sara said, this is the title of my presentation, which is called Thermodynamic Stable Nanovesicles and their use in nanomedicine. This talk would be structured in these four different parts. First, I will start with an introduction. Then I will talk about the quatsomes and you will know what they are. And then after I will explain a few characterization techniques of these nanovesicles, which are these quatsomes. And finally, I will end with the conclusions of this talk. So let's start with the introduction. First of all, I want to start talking about the nanoparticles for biomedical applications. The nanoparticles can be used in different fields in the biomedical applications. But first, I want to start with drug delivery, which is one of the most important, maybe, or most known application of nanoparticles in the biomedical field. First of all, I want to start explaining what happens when an active molecule is administered in our body. And an active molecule alone. In this case, the active molecule would be distributed in all of the body. But imagine that we want to target the pancreas in this case. So the active molecule will reach the pancreas, yes, but also other tissues and other organs. So for this reason, it is important to try to encapsulate the active molecule in a nanoparticle in order to target the specific organ or tissue. So for this reason, the nanoparticles are used in drug delivery field in order to target and also to protect the active molecule. In this case, for example, we can protect the active molecule for our immune system. But also, the nanoparticles can be used in optical bioimaging. For example, imagine that we want to that we want to visualize a cell. In this case, we can use a single fluorophore, which would be excited, and then this fluorophore would emit light. But imagine that now we can put several fluorophores in a nanoparticle. In this case, we will excite also the nanoparticle which contains these dyes, but with the signal that we will read will be enhanced. So for this reason, this is another property, or this is another thing that also the nanoparticles can impact in the biomedical applications. Also, they can be used as optical bioimaging proofs. In this case, here I show different nanoparticles which are classified depending on their material. Also, there are other nanoparticles. Also can be, for example, the first organization is between inorganic and organic nanoparticles. And also depending on the molecules, the organic molecules that compose the nanoparticles can be classified depending on polymer-based nanoparticles, lipid-based nanoparticles, and protein-based nanoparticles. And here in this talk, I will focus on the nanovesicles, which is a kind of lipid-based nanoparticles. And what are nanovesicles? And in this case, nanovesicles are composed by amphiphilic molecules. And an amphiphilic molecule has an hydrophilic head and an hydrophobic tails, which in water, they self-assemble in water and then form these nanovesicles, these closed structures, and in this case, which forms with a closed bilayer, forming finally these nanovesicles, as here you can see some images. In this case, the nanovesicles can be classified depending on their size and also on their number of lamellas, which are these structures. So in this case, this depending, for example, in this case, we have multilamellar vesicles, which are these ones, which are larger, and also they have. Also, we can entrap different vesicles in the same vesicle. So in this case, depending on the size and the number of lamellas, we can have different nanovesicles. And here, the ones that we want to study more, and also the scientific community are interested in the SUVs, small unilamellar vesicles. Why? Because they are small, and also they are more homogeneous. So in this case, we can control better their functionalities. For this reason, the SUVs are the ones that are being used more. Also, as I told, the SUVs can be multifunctional. Imagine here we have a plain nanovesicle, but also this can be modified with different units or different molecules. Here I show some of the functionalities, some of the modifications that can have a SUV. In this case here, you can see that these small unilamellar vesicles can be modified as we desire it, and also they can entrap different molecules. Also, the type of vesicles, depending on the molecules that are composed, they can be classified depending on different types. For example, the most studied nanovesicles are the liposomes, which are composed by phospholipids. However, and also here in this case, you can see that the liposomes are the most used nanoparticles in clinical trials. As you can see, more than the half of the clinical trials are using liposomes. However, these nanoparticles, these liposomes has one important drawback, which is their stability. They tend to interact between them, and finally they coagulate. So because they are thermodynamically stable nanoparticles. And this is a problem because these fact limit their translation from the lab to the clinic. So for this reason, the scientific community tries to develop new thermodynamically stable nanovesicles. And here, for example, are quatsomes, which are thermodynamic stable nanovesicles. But what are quatsomes? Quatsomes are composed by ionic surfactant and sterol derivative. So these two different molecules, for example, the CTAB quatsomes, which are the most studied quatsomes, are composed by CTAB as a surfactant and cholesterol as a sterol derivative. In this case, the two molecules in water behaves completely different. As you can see, the CTAB in water forms micelles. However, the cholesterol in water forms crystal. However, when they are mixed together, they form this closed nanovesicle, this spherical nanovesicle, which is called quatsomes. And here you can see how the cholesterol and the CTAB are structured in the bilayer. So they form this nanovesicle, in this case, these quatsomes. And quatsomes also, as I told you, are composed by ionic surfactants and cholesterol. So depending on the surfactant that we use and also the sterol derivative that we use, for example, we can have cholesterol modified with some targeting unit or PEG molecules. We will have different properties or not regarding on their molecules that are composed. So in this case, I would like to remember that different membrane composition will impact on different quatsomes properties, which is important because depending on the membrane composition, we will have different functionalities of our quatsomes. And with this, I finish the introduction, and I will start with the second part of this talk, which is called quatsomes properties, which I will explain for two types of quatsomes, and also I will explain some of their properties and functionalities of these quatsomes. First of all, I will explain with some characteristics and properties of the CTAB quatsomes, which are composed with the CTAB and as a surfactant and cholesterol as a sterol derivative. In this case, these quatsomes are nano-sized, so they have sizes about 100 nanometers. Also, they are positively charged. They have the CTAB, which has a permanent positive charge. They are homogeneous in terms of vesicle to vesicles. And also, they are thermodynamically stable. They are also stable upon dilution. They can be multifunctional. Also, they can load different proteins. And also, they can be functionalized with protective groups. And these quatsomes currently are being developed as for topical administration as a pharmaceutical drugs. And here I want to show you, first of all, how we know that they are thermodynamically stable, how these quatsomes are thermodynamically stable. In this case, some molecular dynamic simulations has been carried out, in this case, coarse grain simulations, which can allow us to simulate a whole vesicle. And in this case, you can see that they have some defects in the membrane. So they are not spherical. They have some defects, and also these defects can be seen in the cryo-TM images, where you can find that here we have some planar layers. In this case, so these defects is what they produce the quatsomes to be thermodynamic stable. So in this case, the quatsomes, the CTAB quatsomes, are formed of planar bilayers in a phased vesicle with defects, which is these defects gives the quatsomes the property to be thermodynamically stable. So this is an important, which is not the asymmetry, is the defect that gave this property. Also, the quatsomes, the CTAB quatsomes, have been used in topical delivery. They have been developed in order to load EGF, which is an epidermal growth factor, which is a protein. And here you can see like a cryo-TM image, and also they protect the EGF in order to be degraded by a protease. So in this case, the CTAB quatsomes protect the EGFs, and also these quatsomes with EGFs have been integrated in hydrogels. And also you can see that in this graph that the bioactivity of the EGF is enhanced even when the quatsomes are jellified in the hydrogels. So in this case, the CTAB quatsomes are good candidates for topical delivery in order to deliver this EGF protein in the skin. Also, CTAB quatsomes have been used as optical contrast agents. And here I put the FRET. I don't know if you know FRET, but FRET is Forster resonance energy transfer. And this happens when we have two dyes, two fluorescent dyes in close between them. And here, in this case, we load the quatsomes, the CTAB quatsomes, with DII, which is this one, and the DID, which are two carboxamine dyes. And what is FRET? FRET, for example, you need two dyes, one that will be excited, and then this dye will transfer this excitation to another dye, which is the acceptor, and we will read the emission of this second dye in this case. But however, we need to accomplish two things in order to have a FRET. The first of all is the distance between the two dyes should be lower than 10 nanometers, and also the emission of the first dye must be overlapped with the absorption of the second dye, because if not, this energy transfer cannot be occur. And for example, if we increase the distance between the two dyes, then the FRET signal would be lost. So this is an important that the two dyes should be in a shorter distance in order to experience FRET. And with that, we have prepared these quatsomes with these CTV quatsomes with these two dyes, and also we characterize them. And also here you can see in the nanoparticle tracking analysis result that they are homogeneous, and also in the cryo-TM image you can see that they are well, you can see the morphology of these quatsomes. In this case, you can see that they are spherical and homogeneous, and also they have only one lamella. And also in this case, we recorded the emission of the second dye while we excite the first dye. So we excite the DII and we read the emission of the DID if there is FRET. And in this case, in the emission graph, we can see that we can see the emission of the second dye. So we can see the emission of the DID. So we have achieved a FRET. So we have FRET phenomenon in our quatsomes, which this is good because with the FRET, we can reduce the background when we do bioimaging, and also in the bodies or in animals, which there are a lot of background and noise. Here in this case, we will reduce the noise in the background, and also we can monitor the stability of the nanoparticles, in this case the stability of quatsomes, because if we lose the FRET signal, so if we lose the emission of the second dye, here we will know that the quatsomes will be broken, so we can monitor also their stability. And with that, I finish with the CTV quatsomes, and now I will move very briefly to I will show you the MKC quatsomes, another type of quatsomes, and why they are used. In this case, the MKC quatsomes are composed by MKC surfactant, which is another surfactant, which is different also compared to the CTV. But also they share the positive charge, which is permanent, and as a sterol derivative, we have cholesterol. In this case, these MKC quatsomes will be used as intravenous drug delivery systems, but the properties are also they are nano-sized, they are positively charged nanovesicles, also they are homogeneous, and also as they are they can be used in intravenous drug delivery system as intravenous drug delivery systems. They need to accomplish different purpose. In this case, they are stable upon dilution and also in human serum. Also, they are stable in different saline buffers, like for example PBS. And also they are non-toxic in fibroblasts and in mice at the concentration that we used. Also, they are internalized in cells via endocytosis, so they reach the lysosomes. Also, when they are administered in mice, in this case, they are accumulated in the liver of the mice, and also in tumor, in the case that they have tumors, the mice. For this reason, they are being used for intravenous administration purposes. And here I will show you briefly how we know that these MKC quatsomes are intravenous. First of all, in this case, we inject these MKC quatsomes in these mice, which is Swiss new mice, which means that they don't have immune system, and we implanted colorectal tumors in these mice. And also we injected these quatsomes in the mice, and also we studied their with the cells, the histological damage. And we can see that there are no differences between when we inject buffer and when we inject the MKC quatsomes. For this reason, at the dose that we administered, we don't see any damage. So these MKC quatsomes does not affect the cells of the mice in any of the studied organs. And also we analyzed the biodistribution of these quatsomes. As you can see here, we injected 3 different doses, and as you can see that mainly they are localized in the liver and also small part in the tumor. So for this reason, these nanovesicles have good properties to be used in intravenous administration, because they don't present histological damages, and also they biodistribute in the liver and also in the tumor. I would like to remind that these quatsomes, they don't have targeting units, so they are naked quatsomes, so without any specific ligand on the surface. And also another property of these quatsomes is that they can be loaded with some dyes. In this case, we loaded these MKC quatsomes with a DIR dye. This DIR dye emits in the optical transparency window, which means that this emits in the near infrared region, as also you can see here that they emit after 700 nanometers. And this is a good thing, because if we search how a good fluorescent organic nanoparticle should be, here you can see that they should emit in the optical transparency window, because in this case the noise and the autofluorescence is reduced. So here we will not see the autofluorescence of other organs and tissues. For this reason, the MKC quatsomes loaded with near infrared emitting dye are candidates to be used as near infrared optical contrast agents, in this case loaded with DIR, which is also a carboxynin dye. And with that, I finished this part of these quatsomes properties, which I gave only 2 examples that have been developed, and also the ones that are being developed mainly in our lab. And finally, I will show you briefly some techniques of characterization that we have employed in order to characterize the quatsomes. Very briefly, because there are plenty of characterization techniques, and I will show you only some examples. First of all, I will start with light scattering. In this case, I will talk about the dynamic light scattering, or DLS, and the electrophoretic light scattering, or ELS, which are different techniques. But however, these two techniques can be measured with the same instrument, usually known, which is the zetasizer. However, they are two different techniques, and I will show you briefly. First of all, the dynamic light scattering, or the DLS, you have a laser which with a specific wavelength, which impacts on your nanoparticles. And depending on the size of nanoparticles, the fluctuation of the scattered light would be different. In this case, larger particles the scattering will take more time. So the fluctuations along time they would be bigger and more spread. In contrast with the smaller particles, where the fluctuations would be faster. In this case, larger particles will have slower fluctuations on time of the scattered light, while the smaller nanoparticles would the fluctuations would be faster along time. So in this case, the dynamic light scattering measures the Brownian motion, because here with the fluctuations you can relate you can know the Brownian motion. However, remind that what measure the equipment is the Brownian motion, the technique. And with this, we can determine the hydrodynamic diameter. So this is important because this is not the real or the geometric diameter. So also is the hydrodynamic diameter, which also relates with the molecules that surrounds the nanoparticles. And also it determines the polydispersity index, which will give information about the homogeneity of our sample. For example, if we have a sample, a completely homogeneous sample, we will have PDIs of 0. But if the sample is completely heterogeneous, we will have PDIs of 1. And now I will move to the electrophoretic light scattering, or ELIS. In this case, remind that when you have a nanoparticle in solution, also even in water, in pure water, distilled water, the ions present in the solution would be arranged depending on the charge of the nanoparticle. For example, in the case if the nanoparticle is positive, the negative ions would be arranged in the nanoparticles or around the nanoparticle, which is called the Stern layer. And then different layers of different ions, of different charged ions, would be arranged. In this case, for example, if the nanoparticle is positive, then here we will have the negative Stern layer, but then we will have another positive layer, then another negative, and these are called the electrical double layer. And here we will measure the more or less the charge of not the surface charge. We will measure more or less, but in this case is the potential. We will measure the potential, nor the surface potential, neither the Stern potential. We will measure like a little bit inside the electrical double layer. We will measure this potential, which is called the zeta potential. And how it works here is you use the same laser, which also will impact on the nanoparticles, and we will apply an electric field in the suspension. And depending on the scattered light, for example, if the scattered light is more wider than the laser or the incident laser incident wavelength, we will have positive values of charge. However, if the scattered light is shorter in terms of wavelengths, compared to the incident or to the reference beam, we will have negative nanovesicles. And here, so this is important that this technique measures the electrophoretic mobility. And with some equations and some approximations, we will determine the zeta potential, or in brackets, I put the apparent zeta potential in the case that we are not using the correct approximation or the correct equation. So this is important to keep in mind that the LES measures the electrophoretic mobility, and with that we will measure we will determine, the zeta potential or the apparent zeta potential. And the dynamic light scattering and the electrophoretic light scattering are two different techniques which are used which are integrated in the same equipment. However, they are two different techniques. So the DLS does not measure the zeta potential. Is the electrophoretic light scattering which determines the zeta potential. And now I will show you other techniques that we used in our lab, which are the nanoparticle tracking analysis, or NTA, and the cryogenic transmission electron microscopy, or cryo-TM. First, I will start with the NTA. And the NTA also, we have the suspension, and we use an incident laser beam, and then the nanoparticles also, they scatter this incident laser beam, and we detect with a microscope this beam. So as you can see, we record a video, an animated video. It's not an image, this is a video, while we see that these white spots, which are nanoparticles, how they move in the suspension. And with this movement, we can measure, well, as I told you, we measure the nanoparticle movement. And with the movement, we can determine the hydrodynamic diameter and also the concentration of the nanoparticles, because we can count the nanoparticles that are in this frame, and with some approximations and calculations, we can determine the particle concentration. So this is also another technique that can measure the hydrodynamic diameter of our nanoparticle. Also, this is hydrodynamic diameter, which is not the real or the geometric diameter. And in this case, for example, now I move to the other technique, the cryo-TM technique. In this case, we put the cryo-TM, the solution, over a grid which have some holes. So we put the solution, and then fastly we submerge this, we put this grid with our solution in a liquid ethane, which is surrounded by liquid nitrogen. So in this case, we vitrify the suspension. So in this case, the water is vitrified, is amorphous when it's freeze-dried. So this is not crystalline. This is important in order then to visualize the nanoparticles. Then once we have this grid with our solution vitrified, we can put this grid in our microscope, in this case in our TEM, and also we can, we put here our grid, and we visualize our grid. In this case here in the image, we can see that we have small, we have nanoparticles, in this case vesicles, which are not completely spherical, and the big circle that you see here more in black, this is the grid. So in this case, it's important to distinguish the grid and our nanoparticles. So thus, the cryo-TM technique measures an electron density, because in fact this is a TEM, so the TEM measures the density, the electron density, because you are using electrons as lasers. So in this case, it's not optical laser. Here you have an electron gun, and the electrons impacts on our sample, and the different structures that we see here are based on their electron density. And this technique determines the morphology of our nanovesicles in this case, or also other nanoparticles, and also the lamellarity of the vesicles, in this case if they are vesicles, because we can know the number of lamellas that they have. Also, with this technique that I forgot to put here, with this technique we can measure like the geometric size. In this case, because we can measure with some programs, we can measure the size, the geometric size, or the cryo-TM size, because it is important that this will be the size similar to the real one, but maybe it is a little bit different because this is in the conditions of vitrification. So in this case, in frozen or vitrified suspension. And with this, I finished. So I explained very briefly some techniques that we use here. Also, they are physical-chemical techniques that we employ in our lab. And finally, I will move to the conclusions. And I want to put only one conclusion because I want to give you this message, which is this one, that the membrane components impacts on the properties of our nanoparticles. So this is important to design our nanoparticles, or in this case nanovesicles or quatsomes, because depending, for example, as you have seen, depending on the particles that we use, on the membrane components of the quatsomes that we use, we have different quatsomes, which, for example, the CTAB quatsomes are used for topical delivery instead of the MKC quatsomes, which are used in intravenous delivery. So this is important to remind that you need to be careful to decide which are the membrane components or nanoparticle components that you will use in order to have different properties, in this case multifunctional properties. And also surrounding this puzzle are the characterization techniques, which gives information about the membrane components and also the properties. So this puzzle is accomplished also thanks to the characterization techniques, because if not, we don't have any information. And finally, I would like to thank you for for listening me. And here you have my email address if you want to contact me for anything. And thank you again, and thank you.
Thank you, Guillem, for your very nice presentation. It was very detailed and interesting.
Thank you.
Now it's time for questions. If you want, you can ask, or you can write them in the chat and I can read for you. So I don't know, don't be shy if there are some curiosities. Well, I have some curiosity to ask you.
Okay.
As you know, I also work on similar topics, so
Yeah.
I will ask you something general, like, well, you explained a lot the properties of these systems. So, what do you think that are the most important limitations and advantages in the preparation of, for example, a commercial drug starting from systems like this?
Yes, the limitation in this case, also we need to be aware of the molecules itself, because in this case, for example, some surfactants are known as to be toxic. So in this case, one of the limitation is the toxicity. You need to select the appropriate molecules in order to have lower toxicity. For example, the CTAB is not well used, or it is not used for intravenous delivery. However, it is used for topical delivery. So for this reason, it means that the CTAB quatsomes are toxic when they are injected in the blood. However, they are not toxic as well in topical administration. So this maybe is the, well, not the limitation, but is the most important key that you should take into account. And maybe you will have, as you will use some surfactants, and in this case quaternary ammonium surfactant, maybe you will have some drawbacks regarding this, regarding the toxicity. And this is important to keep in mind, that you need to select and also to prove that the quatsomes are not toxic for the purposes. And then the advantage of this system is the homogeneity. These systems are really, really homogeneous. You have PDIs, extremely lower PDIs. In some cases, you reach PDIs of 0.1. So it is close to the zero. So it's a system which is mainly homogeneous. And this is one of the advantages because, for example, if you design a nanoparticle, in this case a quatsome, that will break with an external stimuli like a change of pH, imagine that the nanoparticles are all homogeneous. Then all the particles would be broken when you will change the pH at the specific pH. However, imagine that you have an heterogeneous system. Then if you put a pH, a theoretical pH, maybe only few nanoparticles are broken. So this is important to keep in mind, that the quatsomes are heterogeneous, and this is an important thing of the nanoparticles, of these nanoparticles.
Okay, thank you. Well, you mentioned another important thing, that is the composition of the membrane. So how much is possible to stress the composition? I mean, there are limitations. How much are versatile these systems?
Yes, these systems, I will put like some of the first images, because this is important. That here I want to show you more or less the ionic surfactants. They have an aliphatic chain, this is important. For example, some of the drugs or some of the molecules that you can incorporate inside the bilayer, they should have like this aliphatic chain, because you guarantee that they are internalized in the bilayer. For example, in terms of cholesterol, also, if you want to substitute the sterol derivatives, it is important to have this structure, this kind of a structure. Also, the cholesterol has this, well, cholesterol is an hydrophobic molecule, but it has this OH, which is, this OH will interact with a hydrophilic head of the surfactant. So this is important, that also this, in a small proportion, would be like more polar. So in this case, it is important to notice that if you wanna interact a drug with hydrophobic interactions, the drug should have like this, or one or two hydrophobic tails. However, if you want to interact with an hydrophilic dye, in this case, what we can play is with the charges. In this case, for example, the CTAB and also the NKC has this permanent positive charge. So if you want to interact with for example, a negative protein, you can play with this charge. And for example, imagine that you have a positive drug, and you want to load this positive drug in the quatsomes. Then you will need to think with another molecules. For example, we can use the SDS molecule, which is negative, in order to interact with positive drugs. So we can play also with this. Well, we can play with the charges in order to have these electrostatic interactions. So these are the two limitations. Well, the two things that we need to take into account when we want to interact or to load a drug or a molecule in the quatsomes.
Okay, thank you. So just the last one from my side. What about the preparation technique of this system? Is
Yes.
challenging? Easy?
No, sorry, finish, Sara. No, about the preparation techniques. Quatsomes can be prepared with different techniques. For example, we can some conventional preparation techniques are like, for example, thin film extrusion. We can prepare quatsomes with this technique, and also using sonic shots. Also, we can employ like other techniques. That is the one that we use mainly here in our lab, which use supercritical fluids. So we can prepare quatsomes with supercritical fluids, and also they can be prepared with other techniques. Like recently we have proved that the quatsomes can be prepared with microfluidic systems and other techniques. So quatsomes are really easily to prepare. And also, they are, in this case, the CTAB quatsomes are thermodynamically stable. If you mix cholesterol and CTAB in water in the good proportions, in the future you will obtain, like, they will assemble, and then you will obtain these structure, these quatsomes. So they are really easily to prepare.
So, are there more curiosities? Seems not. If not, thank you again, Guillem, for being here today and for.
Thank you to you to inviting me, Sara. Thank you.
And so, just a bit of information about the next seminar. The title of the next seminar is Carbon Dioxide Capture and Valorization, How Metal Organic Frameworks Can Contribute to Save the Planet, and will be presented by Dr. Patricio Campitelli. So, next Thursday. Bye.
Thank you. Bye.